6, right? 6 different outcomes for that when I roll it. What's the probability that I'm going to get a 1? 1/6, right? So if this is 1, okay, I'm talking about probabilities, 1 represents 100%. The probability of rolling a 1 would be 1/6. What's the probability of rolling a 2? 1/6. 3, 1/6. 4, 1/6. 5, 1/6. They all have equal probabilities, right? Yeah? Okay, that right here, what you're looking at is what's called a probability distribution. Notice that if you look at the area of these rectangles, what's the area of this first rectangle? It's 1 wide and 1/6 tall. So the area of that's 1/6. The area of that one? 1/6. If you add up all these areas, what do you get? 1, right? You get 1. That's not a coincidence. That's actually a property of it. Let me give you a different example. What if I take a bag, or let's take a bucket, okay? And in this bucket, let's say I have 4 green balls in here, whatever, and then I have, let's say, let's go with an easy number. Let's go 2 red ones, all right? I'm going to pick a ball out of here. What's the outcomes? Well, I can get either what? Green or red, right? What's the probability of getting a green if I just like close my eyes and pull? 2/3, right? Because there's 6 balls in here and 4 of them are green, so 4 out of 6, that would be 2/3, right? So if this is 1, the probability of getting a green would be 2/3. The probability of getting a red would be 1/3, right? So the areas of these, 2/3 and 1/3 together add up to be 1 again, don't they? So the sum, if you have any event that occurs, and you talk about the probability of that event, the sum of all of the possible outcomes, the probabilities of all the outcomes must be 1. That's a statistical theory, it's accepted, right? So, think about a function where this is your outcome, and this is your probability, but instead of having discrete random variables, 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, or green or red, imagine it's the ounces in a can, right? Well, then your probability can be any, right? If this is 12 ounces, it can be, your distribution is going to look like this. Now, what about over here? Very small, right? Infinitesimally small. But you can't tell me that it can't be 13, or 14. You have to have a function where the total area under it, the total area would need to be what? 1, right? You need a function where when you look at the area underneath it, you have a total area of 1. Because that would be the sum of all probabilities. That makes sense to you? Well, that function that I had on the board, that ugly one, the area under it is 1. Guaranteed. Every time. Doesn't matter what you do to mu or sigma. You change those, you change the shapes, okay? Even if I change, mu just moves it left and right, so that doesn't change the area. But if I change the sigma, it's going to change the shape, okay? But you're still going to get an area of 1. All probability density function areas equal 1. So that's why they're used in statistics, because the sum of all the areas 1. That means the sum of all the possible events, probability of all the events is 1. I hope that makes some connection to you of why we would want to do an integral ever from negative infinity to infinity, or 0 to infinity. It really ties into statistics really nicely. Okay. One more thing I'll mention, and I promise we'll move on. If I have a coin, right? Let's say I have a fair coin, and I'm about to flip the coin, all right? I've got the coin here, I'm going to flip it. It's going to be heads or tails, right? What's the probability it's going to be heads? 50%. Tails? 50%. Okay, now I flip the coin. All right, what's the probability that it's heads? No. So once the event has occurred, you can't talk about probability anymore. All right? So when we talk about probability, it's always about something that hasn't happened. Once it occurs, you don't talk about probabilities anymore. It is what it is. Now I understand, like, you haven't seen it yet, but I just want to make sure you understand that all probabilities are based on something that hasn't happened. You can't ever look at something that has happened and then base any probability off of that. I remember when I was in Vegas way many years ago, my best friend was losing his ass in Vegas, right? And he had like his last like $100 bill, and the roulette table had been like red, 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 like it just kept on red, 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 red. And so he walked up there and he put it on black, right? And it hit red again. He lost his $100. I couldn't explain to him that, independent events, right? You flip a coin, if it's tails 100 times, then there's no more likelihood the next flip that it's going to be heads, right? Just because it did it 100 times. I mean, that event's over, right? Okay, I'm going off. Let's get back to this. Y'all ready for type 2? Yes? I had one more. No, I think you're okay.
I think we should do another example.
You think you want another example?
Yes.
Yes?
Especially because these will be on the exam.
Yeah, I can do one more. It's going to look somewhat similar, though, I think. Well, I mean, do you want it to have L'Hopital or not? That's really the question. Do you want it to have L'Hopital?
You told us that there wouldn't be anything with L'Hopital on the exam.
Did I? Okay. Well, I guess I'll have to stick with that, huh? How about this one? How about this? That's an improper integral, right? We're going from 1 to infinity. And we're going to start with making a limit, right? Limit t goes to infinity, integral 1 to t, natural log x over x squared dx. All right, we're going to need to go do an indefinite integral. Jeez. All right, how do you want to go after that? Integration by parts again. Okay. What's your u going to be, though? The natural log. And the dx will be, dv will be the x squared dx. Now, you should know that it's natural log because of some of the homework that you've had where, in there, I think there was a test problem like this, no? Quiz problem? I think this was on the test, something like this on the test. Where, was that?
It was in the homework.
Yeah, so it's like if you pick natural log to be this, it's a mess. So if you pick natural log here, it works out nice. So du here is 1 over x dx, and the antiderivative of this is 1/3 x cubed. And things work out real nice because voodoo is just going to, like this 1 over x kills off one of those x's. Yes?
Wouldn't dv be 1 over x squared?
Yeah,
What did I do?
You just put x squared.
the 1 over x squared instead of the
Oh, x to the -2. Thank you. Ooh, I almost messed myself up there. All right, yeah, thank you. That's going to be a huge difference, right? X to the -2.
Yeah.
That was a legitimate brain fart. So what's that antiderivative?
Negative
Negative x
x,
to the -1.
or negative 1 over x.
Or if you want, you could put -1 over x. Now, when I do voodoo, it's still okay because it's still just going to be x to a power. So I can find the antiderivative of that. We good? Okay, so I'm moving on here. This is going to be, let's see, ultraviolet. So -1 over x natural log x minus integral. Voodoo is this times, let's do this one. When I multiply those two together, I have a negative there, right? I'm going to pull the negative out. And when I pull that negative, it's going to make that a plus. And then in here, I will have 1 over x squared dx. That's just those two together, right? Do we know the antiderivative of 1 over x squared? We just did it, right? That's what this was, here to here, right? So we've already done this. This is going to be negative 1 over x, natural log x, minus 1 over x plus some constant. Do I need to clarify anything there? Sure, we're good? Yes?
Why did you sorry, did you erase something between the natural log x plus? You did.
No, I left space, and then I didn't need all that space. So it was originally a minus, right? But then I pulled this negative out, and so it became plus. All right, that's my antiderivative. So this is now going to be limit t goes to infinity. All right, yuck. Negative 1 over x, natural log x minus 1 over x, evaluated from 1 to t. Which equals limit t goes to infinity. Fundamental theorem of calculus. Plug in t first. Negative 1 over t, natural log t minus 1 over t. Plug in 1. Negative 1 over 1 times natural log 1 minus 1 over 1. All right, this is going to turn out to be a number, right? Negative 1, what's natural log of 1? 0. So that's 0 minus 1. So all of this over here becomes minus 1. Okay, so this is nice, right? This is nice. We just got to figure out what's happening over here. And that's going to be a limit I need to look at. Shall we do it right here? So some more scratch work here. What is the limit as t goes to infinity of negative 1 over t, natural log t, minus 1 over t? I think you can do this still with, well, do we need L'Hopital here? I was trying to do one that didn't have L'Hopital. This goes to what? 0. But natural log of infinity, think about the natural log function, what it looks like. This is natural log, right? And as you go to infinity, it grows slowly, but it grows, right? So it goes to infinity as well. So this is 0 times infinity. And then minus, and then 1 over infinity is 0. So again, do you see we still have the problem here? You could try factoring. I don't think that's going to solve the problem, though. Because if you factor out, if you did, like if you pulled the negative 1 over t out, you'd be left with natural log t plus 1. And that goes to 0, and that still goes to infinity plus 1. So you still have infinity times 0. Oh, well. Well, this one's not that bad, though. If we look at that limit, look at this limit. Limit t goes to infinity. I'm going to write it this way. Negative natural log of t over t. I'm going to write it that way. All I'm doing is looking at this one right here. I don't care about that. That goes to 0. That's not a problem. This right here, I'm just going to move the t underneath the natural log t and put the negative up top. Do y'all see that goes to negative infinity on top and infinity on the bottom? So infinity over infinity? So you can use L'Hopital. Derivative of the top, negative 1 over t. Derivative of the bottom is 1. Right? Derivative of natural log of t is 1 over t. Then derivative of t on the bottom is 1. So now if you take this limit, this 1 doesn't even matter. 1 over infinity, that goes to 0. So this is just 0. So we know that this goes to 0, and that also went to 0. 0 minus 0, 0. So what's your answer? It converges to positive 1, right? I didn't put on the last one. I should have written down diverges. I didn't do that, but here I'm going to put converges. Who has a question? I thought I saw this one, and I didn't see that it had L'Hopital in it. I saw it like earlier before class. I looked at some problems because I was trying to look for some intentionally to get L'Hopital. And when I looked at this one, it didn't look like I had L'Hopital, but I guess I do. Questions? No, you just write diverges.
Because there's no possible way to find that answer.
In order for convergence, right? For convergence, you need it to go to a number, a real number, not infinity. Infinity is not a real number, right? A fixed number. So you need it to go to an actual number. If it goes to anything other than a number, like infinity, or even if it oscillates, like let's say we get it, let's say you do a problem, this is going to happen in some of the homework. Let's say you do a limit on one of these problems, and in here you have sine of t. This limit doesn't exist. As t goes to infinity, the sine function just oscillates. It doesn't go to 1, doesn't go to negative 1, doesn't go anywhere in between, it just keeps changing. So that limit would not exist. So therefore you would say that the integral diverges.
We have to prove with L'Hopital's as well.
There's nothing to prove here. We just know that this sine function doesn't head to anything as you go to infinity, right? All right, one more thing. Buzz. All right. Last class, I did 2 examples for you. If you look back in your notes, I did one problem where we did integral from 1 to infinity of 1 over x squared dx. That might have been the first one I did. You can go back and look in your notes. And then I did this one. Can y'all check? I did both of these, right? This one converged, and this one diverged, all right? So this right here is a general formula for what if you have 1 over x to a power, p here stands for power, what will this answer be, all right? Well, it turns out that there are 2 possibilities. It will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. Let's just check that mentally over here. What's p in this problem? 2, right? It's 2? Is 2 bigger than 1? Yeah. This says, well, if p is 2, this should converge, all right? Now this one, what's p? 1, right? The power in that x is 1. 1 is less than or equal to 1, right? So it should diverge. This is just telling you, I haven't proven this to you, but do you understand how to read it? What if we had this? Does that converge or diverge? Why? Why does it diverge? The power on this is 1/2, right? X square root of x is p to the 1/2, or sorry, x to the 1/2. So here p is 1/2. And according to this, which I have not proven, we should have divergence there, right? What about this? So diverge, diverge, converge, right? How about this one? Whoa. How about this? How about x squared? Is this that? You could rewrite that, right? Couldn't you? You could rewrite this as integral 1 to infinity of 1 over x to what power? Negative 2, right? dx. And now p is what? Negative 2. And negative 2 is less than or equal to 1, so it should diverge. That should make sense to you, right? The x squared, think about what that function looks like. And you're going from 1 to infinity and asking for that area. It's divergent, right? It's an infinite area there. Yeah? Yes?
Does it matter if it's just besides 1, is it, would it matter otherwise?
Great question. The question is, if I change this number 1 to another number, does it change the answer? Yes and no. As long as this number is bigger than 0, it doesn't change. All right, so I can make this number 1/2, and I'm still going to get convergence. If I change this to 1/2, I'm still going to get divergence. If I change this to 10 to the 20th power, it's a huge number, right? It's still convergent. If I change this to 10 to the 20th power, huge number, it's still divergent. The thing you can't do is go past 0, because what happens if I plug 0 in here is that now you have division by 0, don't you? And that's type 2. We haven't talked about that yet, but that's a type 2 improper integral, because the 0 causes a problem in here, right? So does that answer your question? Okay, yes?
So on the test, could we use this?
Yes, on the test and in the future, when we get to chapter 8, sequences and series, one of the things we're going to do is something called the integral test. And when we do the integral test, we're going to hope on some of them to have this scenario. And then once we have this scenario, we're going to say, oh, remember this? Oh, p is less than 1. Oh, it diverges, right? So we want to be able to just immediately go to this, right?
Do you still want us to show how it diverges, or can you just put that it diverges?
You can just put that it diverges. That's it. Once you know what p is, you can just tell me what happens. Now, I'm not going to go through the whole demonstration of this, but let me just try and see if I can quickly convince you why this is true. I think it's pretty easy to show. It's just we could take half an hour. I will only take like 5 minutes. All right, the antiderivative of that. So what I would have to do is change it to this. Change it to a limit, right? And I would have to find the antiderivative of 1 over x to the p. Remember, this is really x to the negative p, right? Really? That's what that means? The antiderivative of that is 1 over negative p plus 1, x to the negative p plus 1. And then my evaluation bar, 1 to infinity. 1 to t. Does that make sense to everyone that that's the antiderivative? It's just power rule. So as I now go to the next step, I'm going to plug t into this, right? And once I plug t in for x, I'm going to let t go to infinity. Let's just look at that. What would happen if I take the limit as t goes to infinity of this expression with x replaced with t, right? This right here, the limit is not affecting this, right? And this is just a number. So I'm just going to ignore that. All I'm going to do is look at this piece, and I'm going to replace the x with t. T to the negative p plus 1. So imagine that this t gets huge, right? That t is getting big. Does that go to infinity or does it go to 0? Well, it depends on this power, doesn't it? Like imagine if this power, if negative p plus 1 is bigger than 0, right? If that number is bigger than 0, then it should just blow up, shouldn't it? Like this thing should get huge. But if this number is less than 0, now it's a negative. Imagine this is a negative number, like negative 2. This is really 1 over t squared. And now as t goes to infinity, that goes to 0, doesn't it? So it's like we have two different scenarios. And so if you just solve this for p, this one is 1, p is less than 1. This one right here is p is greater than 1, right? So if p is greater than 1, this thing is going to go to 0. If p is less than 1, this thing is going to blow up. And that's where this comes from. Now, the equals comes from the special case when p is 1. When p is 1, this formula falls apart, doesn't it? But it's natural log. Like, we know that already, and then we can show that natural log diverges. So I hope that's just a sketch of me proving it, okay? I'm not going into detail here, but hopefully that convinces you that, okay, p greater than 1, convergence, less than or equal to 1, divergence. Just use it now, all right? Oh, another thing I forgot to mention, damn it. That standard normal distribution, that ugly formula, that ugly thing that I showed you just a second ago, 1 over square root of 2 pi sigma e to the negative x minus mu squared over 2 sigma squared, this thing. If we were to try and do this, the first step would be for us to find the antiderivative of this. And that is impossible for us to do. Right? That function, the standard normal distribution, the antiderivative, we have no technique of integration in this class that we've learned to handle that integral. There are certain integrals right now that we can't handle. They are, I'm going to show you a very simple version of it. If I asked you for this right now, this is a classic example. If I asked you, just give me the antiderivative of that, whoa, we're stuck, okay? We can't do it. Not only can we not do it, Wolfram can't do it either, all right? So if I do in here antiderivative of e raised to the negative x squared, we are going to get 1 over 2 times the square root of pi times erf x. What's erf? Erf is an error function. So that's basically the computer saying, hey, look, I can't do it, all right? I can't do it. So we get to this situation where it's like this very important function, because basically this is this. This really important function in math, we can't even find the antiderivative of it, right? So we're like, well, what the hell? Well, in the real world, if you were to take a bucket, right, that has all the functions in it, right, the bucket of all functions, and you were to reach in there and grab a function randomly. Remember my thing where you grab a number off the number line? Remember that story I told you? Okay, same idea. If I were to close my eyes, pick a function out of here, the probability that we can actually integrate that by hand using the techniques we've learned is essentially 0. All right? Which is why Chapter 8 is so important. Because in Chapter 8, we learn that there's another way to represent this function. We can represent this function in what's called its power series. And once you turn it into its power series, then you can integrate it. All right? And it was Newton in the power series. There's 2 fathers of calculus, right? There's Isaac Newton created calculus, and there's Leibniz. Leibniz was the other father of calculus. They both developed it. Same point in history. They created calculus. They didn't know of each other, so the story goes. And the big difference between the two was that Newton had power series, and Leibniz didn't. So with power series, you can still handle this. Leibniz was dead in the water here. Newton could keep going. So if I go back to this and scroll down, I bet you anything there's going to be something about this in a power series. Let me just scroll down. There it is, right there. See that series expansion? Right there? That x minus x cubed over 3 plus x to the 5th over 10? That, right now, that makes no sense to you. We will be able to get that, and we'll make sense of what it means and everything else later, all right? So even though we can't do this by hand, right? I'll pick it up. We can't do it by hand. I convert it. I do its power series. Then I can do it. And that's the way computers work. That's the way your calculator works. When you type into your calculator, I'm going off now, I'm sorry. When you type into your calculator sine of 2, what does your calculator do? It has no freaking idea what the sine function is. It doesn't know what a unit circle is. It doesn't know SOHCAHTOA. has no idea of a right triangle. What is your calculator actually doing? It's plugging the number 2 into something, right? That's all it's doing. It's taking the number and it's doing something with the number 2. What it's doing is it's plugging it into this formula. This right here. Let me think. This. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Have you ever seen these exclamation points? If you haven't, this is what they mean. 3 factorial means 3 times 2 times 1. 5 factorial means 5 times 4 times 3 times 2 times 1. This keeps going forever. So when you type into your calculator, if you're in radian mode and you type in sine of 2, your calculator plugs in a 2 here, 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 and it probably, whoever programmed the computer probably told it to go out like maybe like 30 of these and then stop. And then it returns that answer to you. So what the hell is this? Well, this is what we call the power series for sine. Actually, it's called the Maclaurin series, but this is what I'm talking about. Every function, this is what sine of x is, okay? You learned sine of x in pre-cal, right? In Cal 2, this is what sine of x is. Not yet, chapter 8, this is what sine of x becomes, all right? Every function has a power series. And that's what a computer sees, all right? One last thing. Is sine an even or an odd function? Do you remember that definition, even and odd? It's odd. Do you notice anything about its power series? They're all odd powers of x. Cosine is an even function and its power series has all even powers of x. Okay, I'm getting way ahead of ourselves. That's some fun stuff though, all right? Chapter 8 is hard, but it's worth it. It's worth it. At the end, it's what makes us be able to do a majority of what we can do in engineering on computers, is that everything can be converted to a power series. All right, we ready for type 2? Type 2. So improper integrals. Type 2. Infinite integrands. Type 1 was called infinite intervals. That's because our interval that we are integrating over was either going like from 1 to infinity or negative infinity to 1 or maybe negative infinity to infinity. So the interval, right, that we were looking at was infinite. Type 2, it's the integrand that's infinite. That's the thing, that's the function inside. So I'll give you a quick example. All right, I want you to look at that, and I want you all to compare that. You know what, let's do x squared.